Okay, welcome back Science 30s to our next lesson in chemistry. Today we are looking at 1.4 and talking about acids and bases. Out of all the chemistry topics that we talk about in a classroom, acids and bases seems to be one of the more common topics that people know about outside of school and in their daily lives. And this might be because of some of the warning labels like this that warn us of acids, or maybe it's that we remember experiments from school like when we take vinegar and baking soda and react them in an acid-base reaction. Now, it can be tough to tell between some acids that aren't so dangerous, things like vinegar and citric acid that might be in your food, compared to these warning labels about these really strong acids that can be quite dangerous. So to figure out the level of acids and the level of danger they can have, let's look into what are acids and also their counterpart, what are bases. So to begin this lesson, you probably looked at the Arrhenius definition from previous science courses. And this was that an acid was a chemical that would create H plus ions in solution, and a base was a chemical that made OH minus ions in solution. That was our acid and base. And that meant that if we had a beaker of water and we're going to take a common acid like hydrochloric acid and put it into water, it dissolves like we saw in the previous video and breaks up into H plus and Cl minus. Now that presence of the H plus was what we said was making this solution an acid, okay, making that H plus ions. And then if we took a base, something like LiOH or lithium hydroxide, we put it into the solution, it's going to break up into Li plus and OH minus. And then it was the hydroxide that was making this a base. The OH minus was our indicator there that this was a base. But in this course, we're going to look at this new definition, the Bronsted Lowry definition of acid and base, which was credited to these scientists. Here's Bronsted and Lowry. It's a little bit more accurate description than our last one, and it's going to describe what happens with that H plus. So let's see what their definition is. It's that an acid is not just increasing H plus, it describes it as being a proton donor. Pretty similar definition there, but they describe it as a proton donor. And then the base being the opposite is a proton acceptor. Okay, so acids give protons and bases take protons. We're going to see that compared to that Arrhenius definition, this is going to allow it so we don't necessarily need a hydroxide to be a base. And we know there are lots of chemicals that don't have an ionic compound with hydroxide and they still act as bases. So this is going to give us a better description of what's going on and allow us to understand why those other chemicals are bases, even though they don't have hydroxide. So to understand what we mean by proton donor and acceptor, let's first look at what a proton is. A proton is the same as H plus. Okay, so we get that from if we're looking at a hydrogen atom and we look on the periodic table, hydrogen has one proton, remember that's the atomic number, and it has atomic mass of 1. Okay, so that means that there's one thing in the nucleus and it's got one proton. So all that's in the nucleus is just one proton. So it's going to look like that. Now normally for a hydrogen atom, there's going to be an electron and it's going to be orbiting around the outside. It's got one plus and one minus. But if we remove that electron and get that out of there, all we have left over is the one proton. So H plus, because we got rid of the minus, is just a proton. So now looking at the definition of proton donor and proton acceptor, we can think of an acid as something that has a proton and can give it to a base. The acid donates and the base is going to be accepting that proton, H plus. And because we're going to be talking about what acids and bases do in water, let's first take a look at water. If I have a beaker of water, almost all of it is going to be these molecules. We have one oxygen and two hydrogens. So we're just going to put a bunch of those. That's the most, what most molecules of water look like. But as I put in the notes there, a little bit, just a couple of them are going to break up into OH minus and H3O plus, what's called a hydroxide ion and hydronium ion. Okay, so what that looks like is if we have this molecule here, we have two of them there, two waters, the H on one of them is going to leave and go on to the next one. So that's left this one as one H less, so just OH, and the other one as an extra H, H3O. Now that H was an H plus, so it's H3O plus because it gained a positive charge, and this is OH minus because it lost a positive charge. Now again, this isn't all of the water molecules, it's only a small amount of them, but they're going to be breaking into this OH minus and H3O plus ions. So now with our definition and knowing what's happening in the water, let's look at how the previous HCl and lithium hydroxide would act with our new definition of proton donor and acceptor. So I'm going to put up two beakers here, and again I'm going to start with mostly water, but I've highlighted in red there the hydronium, H3O plus, and in blue there the OH minus or hydroxide. This is not proportional. Again, there's very few of the H3O plus and the OH minus, but it shows that we have a little bit of each of those, as well as lots of water molecules. Now let's look at what happens when we add the HCl. So we put the HCl in, it breaks up into H plus and Cl minus, and remember that H plus is a proton. The HCl gives that proton to the water. So that's going to go over to a water molecule and turn into H3O plus. It's donated a proton to the water, and now we're getting more H3O plus or hydronium ions. Okay, so then HCl would be called a proton donor, giving H pluses. Now let's look what happens with a base, with the LiOH. And now what's going to happen is that OH minus, that hydroxide, right, this minus charge, can take a proton to become water. So it's going to go over to the hydronium, which remember has an extra H plus, take it away and turn this into two H2O. I realize I only put one there, but that would turn OH minus and H3O plus into two water molecules. So it took the proton from the hydronium. That would make the lithium hydroxide a base because it takes away or accepts protons. Okay, so I hope that theory is making sense for you, and now let's apply it to some chemical reactions. So the first one I have here is with the HCl and water. I'm going to put some diagrams of what these atoms are going to be kind of animated to look like here. So let's put HCl as an H and a Cl. I put the Cl as this big purple molecule and the H as a small blue circle. And then your H2O, kind of similar to what we had before there. Remember the small blue circles are hydrogens, the large blue one is the oxygen. And what this is going to form is then hydronium and Cl minus, because we can see that the hydronium is the same water as we had, but one of the hydrogens has come off of the Cl and been given or donated to that water. So now it's H3O plus because it took an H plus. And then that leaves just left over the chlorine on its own, which is just Cl minus again because it lost an H plus. So now it's got a negative charge. Let's now look at another reaction. This one is of a base, but this time I've chosen one that's not lithium hydroxide. It's not that same OH that we were able to recognize with the Arrhenius definition. This is NH3, so it doesn't maybe look like a base based off its formula, but it's going to act like one, as we're going to see that it's going to accept or take a proton. So we see NH3 plus H2O goes to NH4. So NH3 to NH4, it has taken an H plus, a proton. So to draw here, let's say the N is that yellow circle, and it's got 3 hydrogens, mixes with the water, then it takes one more hydrogen, so it's got 4 of them there. Where to get it from, it took it from the water, so now the water is just one H and an O, which is left over as a hydroxide. Okay, so it took, the NH3 took a proton, so it is a base. So questions like this in your practice questions may get you to label the acid and the base. So we would label the HCl as the acid because it gave the proton, and the water is acting as the base here because it took the proton. We often don't think of water as an acid or a base because it's more neutral, but it can act as an acid or a base depending on what it's mixed with. In this case, it's the one taking the proton, so it's the base. In the one down here, the water is acting like an acid because it's giving its proton to NH3. Okay, so it's acting like an acid here, and NH3 is acting like the base. Now, just before we conclude this lesson, there's one other part that you may have to label, and it's called the conjugate acid and the conjugate base. So let's start by looking up at the top reaction here, and notice that when the hydrogen was given to water, it's H3O plus. So the water has taken that proton, just like if I took this mouse and I'm holding on to it. Okay, so it's holding on to that extra proton. Now it has the potential that it could give that proton back to the HCl. So if he could give it back, that means he could act like an acid and donate a proton, okay, to go in the reverse reaction. So if I put an arrow going the opposite way here, I think I put one there, I could call this an acid if it was going the opposite way. So I write it as conjugate acid. It's kind of like our resulting acid. Now that it has an extra proton, it could give it back and be a proton donor. Very similarly, the Cl has lost a proton. It might want to take one back now. So it gave its proton up as an acid, but if it ever takes it back, it would be acting as a base. So we call it a conjugate base. We can apply this to the second example as well. We see that NH4 plus has taken a proton, just like it takes this. So it's acted like a base because it took a proton. It could give it back. And again, giving is an acid. So it could be labeled, if we have the reverse direction, as a conjugate acid. It's our acid product. And then the OH, similarly, it gave away its proton. So if it went to take it back and take a proton or accept a proton, it could act as a proton acceptor or a base. So that's what you can expect on your practice questions, labeling the acid, base, conjugate base, and then other theory questions on acids and bases. I hope that helped you to understand this and complete those practice questions. Let me know if you have any questions in the live time. Thank you so much for watching this video, and I will see you in the next lesson.